Good morning. How are we all doing today? All right, it is just about time to get going. Excuse me. Hey, we have people in the room now. I had one or two before. Oh, yes. We have emotes. That's right. Let's start off the party. There we go. Cool. All right. Let's get going. How we all doing today? Doing good. Good. Phenomenal. Oh, even better. I am utterly exhausted for some reason, and I do not know why. It's like my third cup of coffee. So, today should be hopefully interesting for you. We're getting into the actual meat of some of the software engineering things. I don't know if any of you were here. I know that Mr. Firehead was there on Wednesday afternoon. We started getting our first trolls in the stream, so that was fun. I popped up on an algorithm, I think, so have to keep an eye on the chat a little bit closely today. But we had some interesting people dropping in. So today, I want to remind you, since Still haven't figured out a good way to get you all reminders in Blackboard. Homework's due tonight if you have forgotten about it. Again, it's just this little Git, learn Git branching tutorial thing, just mainly to get you into the idea of it. And this weekend I will put up the second half of the assignment where classic 10 a.m. Oh, it was 1 p.m. The Twitch trolls dropped by. Somebody was telling me I had to play more COD. Yeah, I don't think I've played COD since my brother had the first zombies, whatever the one that had zombies in it. I realized how awful I am with controllers. More of a keyboard and mouse kind of person. Um, so what we're going to do today, World at War, thank you. Yeah. We're going to go over some basic software engineering stuff. And at 10:40, what I'd like somebody to do is to stop me because boop, boop, boop. I'm going to show you what our Git environment is and how I will be using it. Now, the instructions I'm going to provide you for getting up and going with Git are going to be not sparse, but I'm going to give you the instructions that I would use on the terminal. If you are not comfortable with the terminal, I'm going to provide a handful of like tutorials for how to use a GUI-based environment. So there are Git plugins for VS Code, for Visual Studio, for Eclipse or Mono, or whichever one you're going to end up using. But there are just so many ways to do it out there that I think any kind of a lab manual would be about 30 pages long if I wrote one up for every single environment. So again, feel free to use whatever technology you want. I mean, you can even use the website, worst case, and use it that way, but um, I'll basically show you what we have going on in a little bit. So we have the homework tonight, and if you do not have a group, again, please try to, I guess if you didn't have a group, is there any chance that you found one? If not, I'll just I guess I'll message those of you that tried to get a hold of me later, and I'll see where you're at after class. Um, Otherwise, I'm just going to randomly drop you in a room. So we have a Git demo. We also have a new aspect ratio here, which is just lovely. Um, Honestly, should have like some kind of a silly animation playing in the sides here. But we have our first set of slides that I didn't create, and I was considering heavily modifying them, and then I realized that probably wouldn't be too good since these are like canonical software engineering class slides. So some of them are a little bit dry. Forewarning, there are some interesting uses of old clip art in here, which is a lot of fun. So this gives you the historical view of software engineering classes. So we have a handful of these. These are what you need to know to get up and running with software engineering. So just a forewarning for you. This comes out of somebody else's book. And between Professor DeVries and myself, we've changed this, updated them over the years, but I didn't get to changing the aspect ratio. It looks pretty bad stretched out. So what we're going to go over today, basically, we've been doing all the case studies, we've been scaring you straight, more or less, and now you actually have to see what software engineering is. And what it's going to boil down to is the process. The process, the process, the process. Okay. Good software engineering follows a process. The interesting thing is that we don't necessarily care which process it is, as long as it fits your environment. I'm sure you have all probably heard of agile processes by now. It's the biggest buzzword in industry. Um, if you are working or have worked, you may have used some kind of a process. Like there's the waterfall model, there's agile, there's rapid application development. There are so many that are out there, and it depends on your environment. Nope. Ooh, good. Well, this will be new stuff for you then. Um, Basically, it's just how your team builds software and how you handle development, how you handle requirements, solicitation, testing, maintenance, all of this stuff. It's all going to have the same idea. It's just you're going to move pieces around differently based on what your process is. So this is kind of a historical view slash what you need to know to get into software engineering. You already got all the case studies, so we're going to kind of skip through the Ariane 5 rocket explosion, which is part of these slides, which is kind of towards at the end. But we're going to see how things have changed over the years. So software development, software products, whether it's big or small, they're going to be complicated, right? And if it's a simple little phone app, there's still so many things under the hood that go into building software. A hello world depends on being able to draw to the screen and handle strings, handle characters, and all that. And then you get very massive, complicated software like an operating system or a web browser or Streamlabs, which I have on the screen. So there's a ton of things that go into it. Right, and it's not just writing software. I'm going to keep saying this over and over and over. Software engineering and software development is like 10 to 20% writing code. The rest of it's going to be all in managing that, making sure it works correctly, and that your clients are happy, for instance. So we have two views of software development. We have analysis and synthesis. So analysis is where we're going to take some kind of a problem and decompose it into subproblems. This is one of those high-level theoretical boxy diagrams where there's no actual problem in here. But, I want to build a user registration system for a website. That is my problem. What do I have to do to build that? Well, I need to handle forms. I need to do validation. I need to make sure there's no cross-site scripting attacks. I need to make sure that all of these little pieces are in place before I can solve this problem. All right, so what are all the key issues you have to deal with over the course of the project? So again, these all kind of fit together. And then synthesis, this is the other view of things. I could have N solutions, right? Maybe I want to use React. Maybe I want to use Cake PHP. I want to do raw HTML and jQuery. So I've got all of these possible solutions to solving this problem, however ethereal it may be. And then I'm going to try to compose them together, right? So what do I need? Which Stack Overflow answers do I need to copy and paste over to make my solution feasible, right? So kind of high level here. But what we have is this notion that we're breaking problems down, or we are trying to figure out which solution is most relevant to our problem. So that's what software engineering really is formalizing this whole process. So there's some definitions here in very poorly spaced, nice blue font here. Basically what we have is we have some kind of a method, which is going to be the procedure for accomplishing this goal. I'm not going to read these all because, I know you can all read, but the point is we're going to have these methods. We'll have tools that we use to solve problems. We're going to have to follow a procedure to use the tools to apply them to the method. And then one kind of key factor that you will have too is a paradigm. And this is going to be how your project team, your business unit, whatever group you're a part of, how they are solving a problem. And if one of you is doing object-oriented development and one of you wants to go procedural programming, one of you wants to use something crazy like a functional language, we're going to have team problems there, right? So you have to have a core, path. Looking at some of your project team chats, you're all kind of agreeing and coming to a common solution for your problem, right? Right now you're all focusing on what language you want to use, what tools you want to use, and you're kind of building up from what you know and trying to figure out how you can explore the space of these interests, right? So you're figuring out your tools and your paradigms and all that to slap the really boring academic-y sounding terms on making something cool, right? So why are you in this class? Week and a half into it, 2 weeks now. Computer science versus software engineering. So just to differentiate, again, CS, you're going to get all of your core aspects, right? Your operating systems, your networking, and all of that fun stuff. Here we're trying to figure out how to apply all of these theoretical issues to real world problems, basically. So how are you going to solve these issues? Excuse Excuse me. And one other thing that we have here too is that one of the biggest aspects that we will have in software engineering to deal with is a customer. So in computer science, I might be building software just for the fun of it, right? Or I might be exploring something theoretical. Software engineering, you get into the real world things. You may have a customer or a client or some kind of a stakeholder where they have a problem they want to solve, right? And here in this class, I'm your customer, right? I want you to build me a term project. I want you to scope it out. I want you to define the requirements. I want you to go through this whole process and then deliver a package at the end of the semester with all the artifacts, with the prototype. Okay, have fun. We have all of these things that we have to do. So consider software engineering to be bridging the gap between industry and theoretical here. So we're looking at success stories. You have all seen the catastrophic failures so far. There are so many good success stories to mitigate those things, right? So look at kind of the mundane tasks that we have now, word processors, spreadsheets, email. All of these things we can do in the cloud, right? We can speak with the International Space Station through Twitter or live streams, which is amazing if you think about it from 20 years ago or even 10 years ago. We've had advances in agriculture. There have been algorithms used to automatically figure out where to plant certain crops to get maximum yield based on, okay, the runoff from the cows will fertilize the crop or fertilize the corn versus blah, 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 blah. So something they actually did at Michigan State, which I thought was kind of interesting. So it's not all bad, is kind of the point. We have had a lot of good things. Okay, however, we do have problems, and this is kind of where we need to start formally defining what a problem is. We see the explosions, we see the crashes, and we wonder what causes them. So we have multiple things going on here, but at the end of the day, we have faults, we have errors, and we have failures. So these are some key terms here. So a failure is when we have a system that is supposed to be doing something and it deviates from that. Right, so this could be the presence of a bug. This is our lovely clip art, which I was telling you about. We might have human error where there is a fault by a human being caused, or maybe there's a fault in some kind of internal logic. But basically, we have problems that are occurring because of probably our users or some kind of a bug. More often than not, it's human error, honestly. So this is where we're going to kind of glide through some of the examples, honestly. So we talked about Therac, we talked about Ariana later on. IRS had issues where they lost tons and tons and tons of money because of an automated system that was built. So again, we have problems, but we also have good solutions. All right, so just kind of setting the stage here. So when we get into the notion of software engineering, we have to consider the ideas of quality, of what makes software good and rigorous and well-defined and things of that nature. So we have different views of products here. So a transcendental view, this sounds beautiful, right? Lovely, lovely software. We have quality, meaning that software is good, and we know that it's good, but we're not really sure why. That's kind of like our godlike view of it's just working perfectly, right? We have a user view. So the quality means that software is doing what it should, and I'm happy with it. You have the manufacturer's perspective. So perhaps people building out machines that have your software on it, or your business, for instance. Quality is going to conform to the spec that you have. So your software is doing what you're saying it should be doing. You have your product view, where your performance of your software is tied to the product. And then you have your value base too, which means that my software is good and I can get people to pay for it. It's so good, right? You can think of this almost like the App Store, right? Where I build something and there's a lot of inherent value in that. Before the market got flooded anyway, and now it's hard to sell anything on the App Store. Okie dokie. So, good software. Basically, we're reiterating some points here. we should be striving for quality, and we're going to have competing concerns with what quality means. And, we will be getting to that. You're going to have to effectively satisfy your users, satisfy your management, your clients. So there's a whole range of people that you will have to satisfy in this domain. So if we look at it, and I realize I should have more text in here or more images in here because this just looks awful from a viewer perspective. Um, we're going to have to consider this from different points. And again, people, depending on what their role is, what kind of a stake they're holding in your project, they're going to look at different aspects. Users are going to look at the user experience, if it's failing on them or not, right? Designers and maintainers, these are people more internal. They're going to be looking for, did this trigger a fault? And we've logged the fault, and then we have to go back and fix it. Um, the business leaders are going to be look at our return on investment and things of that nature. So while I have you all here, I'm curious, does anybody know what a stakeholder is? Because this is a term I'm going to keep using over and over again, um, and it has a very particular meaning. Does anybody in the chat know that one? Someone who has interest in something. Stocks. Um, Waiter at Outbacks. Ah, nice. Investment. Yeah, so let me take all of those and put them together. So a stakeholder, I could see the stock idea. But yeah, it's somebody who has an interest in something. So for a project, a stakeholder is going to be anybody tied to the project. This is not just your client. It's going to be the developer, the maintainer, your quality person, your manager, business, project leaders. So basically anybody who is tied to a project is a stakeholder. And what we'll be getting to when we talk about requirements and goals and all the different models that you're going to have to create, stakeholders are going to have different interests and they're going to need different artifacts. Okay. So the idea of a stakeholder is fairly important because these are all stakeholders. They're going to have different concerns for your project, right? So when we talk about software too, we're going to be talking about modeling, and you may or may not have heard of UML modeling. If you did Java, I'm not really sure if you got into like class diagrams or anything of that nature. But basically, you're going to be creating different models of software, which will be showing you exactly what things should be doing at a higher level. And the goal of a good developer is to take these models and translate them to code. In this class, we're not going to necessarily be using a formal, rigorous modeling process. I'm going to be more looking for you to draw boxes and draw lines connecting things. But if you get a very good and rigorous formal model, you can take that and automatically create code out of it based on what the model, like the meta attributes of a particular model. It's like if you whip up a nifty class diagram in one of the modeling languages, you can, in theory, plop that into a tool and generate, here's all my Java code. Or you can take your Java docs and automatically create requirements and things of that nature. So we may look at some of that stuff later, time dependent, but the high level stuff we actually need to cover first. Okie dokie. So moving on, we have different models for process improvement. So this is more than likely these are terms you'll hear if you start working in industry. We're not necessarily going to cover them in too much detail here, but we have different models for improving software. We have governing bodies, so ISO will release specifications for software. You may have to have a particular spice level for your software. It just depends on what you're building. And I'm just going to leave these here for now, but consider that you might have to be ISO certified if your software is going to be safety critical, for instance, like if it's running on a car. And now we talk about some of the things which are horrible as a developer to think about, but if you're going into information systems or quality assurance or business, the notion of a return on investment. This is a frightening thing for a developer because it means you have to tie all of the fun parts to making money, um, which in that case is always kind of difficult to swallow because you just want to write code and build that up. But return on investment, you have to consider trade-offs like how long development will take, how much maintenance will cost, what your staffing plan is going to be, how many developers you need to hire, how many testers. So basically you have this whole there's a whole laundry list of formulas to calculate based on how much it costs to hire all these people to maintain everything. At year 10, we may start making money back on it. But again, if you're getting into the business side of things, this is more going to be your focus here. So consider it in terms of productivity, reducing costs, savings. If you're going into an R&D environment, return on investment is going to be very low for a long time. If you're going into something very product-centric, you'll probably have a very high return on investment. Things to consider if you want to go more managerial, I suppose. Alrighty, where are we at in terms of slide number? So I don't want to overrun my time here. We are about halfway done. Okay, not too bad. Got too many things up on my screen. Okay, so who is doing the software engineering? I'm going to throw a bunch of terms around and I already have a little bit, right? Customer is the person who is paying for the software, whether it is an external entity, whether it is an internal entity. So you may have a business unit that needs software. Customer is going to be the person fronting the money for it, right? So we have to satisfy the customer, make sure that they're happy with their investment. The developer, this is what you normally think of in terms of software engineering, right? The people writing the code, but these are also going to be the people maintaining it and testing it and things of that nature. And then users, not always customers, these are going to be the people actually using the system. This is the feedback you're going to be needing for user experience, for ease of use, for making sure you're not seeing any weird faults in the field, things of that nature. More clip art. So again, stakeholders is going to be anybody with an investment in your system, whether it's mental or monetary. Effectively the same thing that I just talked about, but we have ties in between customers, developers, and users, and poor developer, super pixelated, looks just really, really stressed out, right? All right, out of curiosity, this picture, is this too dated for all of you? Or do we all remember strong bad emails? I didn't want to put the GIF on there for fear that somebody would have a seizure at home. No idea. Okay, this was probably in the late 90s, maybe early 2000s, so no, it would have been early 2000s, mid 2000s, because I think I was an undergrad when this came out. Okay, look up strong bad emails. You look for a nice slice of internet history. Anyway, software engineering, another thing that we can consider is a system level approach. So we're not just going to consider writing code. We're going to have to consider people, which is the worst thing in the world to consider as somebody who wants to sit and just write code. You have to consider the interactions with hardware, with other software packages. So how well does your module fit in with the rest of the system? What are the inputs? What are the outputs? What are the boundaries of your software package? Is that an extra credit homework assignment? That's a good question. I'll have to think about that. We also might have systems that are nested, right? So my software system may be the kernel of another software system, and then you're going to have something that is a wrapper on top of that. And again, we're going to have to be tracking inputs and outputs and making sure everybody is happy. Not sure what's going on today. Sorry about that. So when we talk about systems, and you're going to get another nice bit of clip art here of the human body, a system is going to have different attributes. So it's going to have activities, it's going to have objects, and it's going to have relationships and boundaries. So an activity, think of this like a method, right? A procedure. It is some function that is happening. it may or may not be initiated by some kind of a trigger as well, right? So if it's object oriented or not, right? Objects and entities, these are going to be things in your system or elements. Basically, they're going to interact in some way. Could be a text box, could be a user event or something of that nature. Relationships, this is kind of the hard one to get your mind around if you're not into the notion of, object oriented or anything like that. But basically, you're going to have references between objects. You're going to have objects that are doing their own thing in parallel, and then the actions of one may impact the actions of another. And you have to make sure that you're handling that. And then our boundaries, these are very important because it tells you where your system ends, right? Once I put data out, make it callable by an API or something like that, my data's out in the world, that's where I am done. But I still have to define what these paths are doing here. So if you need to contextualize a system, think of the human body. This is a great system. It is a system of systems, right? So my job here is a human body, and we're just focusing on the respiratory system here. I have to inhale gas, I have to filter it, I have to exhale, I have to take all the good stuff out of the air and bring it into my bloodstream. Our entities in here, these are going to be all of your aspects of the system. So oxygen, CO2, water, nitrogen, your nose, your mouth, your lungs. So all of these things, all of these entities are part of the system. And since we're focusing on the respiratory system here, here's your boundary, right? Your nose, your mouth, your lungs. These are all parts of your system. All right, so kind of a ham-fisted view of what a system is. You care about it in terms of a computer system, right? So here, again, more clip art. Love the clip art. Basically, this is a paycheck production system. Okay, so you have a computer. You might have a mail room where your physical paycheck goes in, if anybody still gets those. We need to validate the date on your paycheck. We need to print the paycheck. We need to calculate how much you made for this period. We have a boundary around the system. We have data coming in from the computer. So this is going to be your payroll staff are inputting all your information in. Everything's happening inside of here, and then coming out is a physical paycheck, right? Now you can replace this obviously with an e-transfer of money to your account, in your direct deposit, things of that nature too. But still a good notion of a system. Data in, stuff happens inside of here, data out. Everything is formalized. We know how every bit of data is being tracked. Okay, so still fairly high level, but what I'm trying to get you to consider are the intricacies of data flow and system objects and functions and things of this nature. Concepts you know from programming, but concepts which actually form the system as a whole. My kids thinks this is the funniest thing that I'm talking to the computer. And when I talked about a system of systems before too, they may encapsulate each other. They may be separate but still dependent. This is where boundaries and relationships come into play. So next, we have this lovely image. So those of you that have taken like a CS 101, 102, do they still talk about the onion model in those classes at all? For what a computing system is? The reason I ask is that was a big thing when I was an undergrad, and I thought it was the most trite notion of computing. We all know that only ogres have layers. But here we have a layered system where basically all of these circles are just different layers of a system. So the core here, we want to remotely collect data. So maybe this is a controller for an IoT sensor network. I've seen them where they're like monitoring earthquakes and things of that nature, right? So I'm collecting some kind of data. Well, this is a core system, but I also need a system to do calculations for maybe filtering data, for handling noise, for converting from units and things of that nature. Well, that's fine, but I also need a system to handle communication. So I need some kind of an architecture to handle, whether I'm bouncing a signal to a satellite or to a cell network from this remote site to my central site. Well, even then, the local site needs some kind of a system, and then that data has to be reported out. So you can basically see that these all are interrelated. We're going to have notions of how they all connect, but these are all technically separate systems. And we're building up with this kind of a layered model. You can even extrapolate that this, we could have multiple versions of these too for maybe different global sites where they're all separate systems of systems, but they're still interconnected. So things will build up. I'm just going to kind of zip through the animations here. So with all of this, and where we start getting into the process for software engineering, we're going to have these key aspects. So you're going to have to build requirements. These are where you specify in natural language, meaning English or whatever your language of choice is, the core functionalities of your system, right? You need some kind of prose that exactly specifies what a particular feature is doing. There should be no ambiguity in requirements. If you know Agile, you might have heard of things like user stories, things of that nature. Those are a little bit more, not nebulous, but more fluffy. In a way you're just describing a feature, there shouldn't be a hard requirement there. I'm going to talk about your system design and your program design. These are more high-level activities where you're kind of scoping out the different pieces of your system. Let me skip writing the programs for a moment. Then you're going to, after you do your design, your requirements analysis, you're also going to have to talk about maintenance, about verification and validation. These are your unit tests, which you're checking your functions, your integration tests, where you're checking your system meshed with other systems, your delivery, where you give it to your client or your customer, and then they do their, and we do testing with them. Maintenance, where you keep up with your software, make sure that it's still functioning as expected. Kind of why I skipped writing the programs is that this is like one of the smallest pieces of the whole process, right? All of these bullets here is software engineering, right? This is our process. Implementation is a tiny little bit. And the reason why I keep saying that is writing code is easy, more or less, right? I mean, obviously it's hard if you're learning how to program, but it's a technical, mechanical process. The hard part is the mental analysis, right? What are my requirements? What is the software going to do? What are all the situations it's going to experience over time? The programming is just taking all the hard work that you've already done and just making it happen, right? And I'm going to say, making it happen like it's a magical, easy process. Obviously, it takes a long time to write a program, but it's not always the hardest part. You're all going to disagree with me as you work on your term projects, though. Okie doke. So who works on development? So we have all of these different roles in the software engineering team. Programmers are just the people writing the code generally. And we should separate all of these roles nicely because you don't want one person doing the testing and the development and the maintenance. We saw this with our catastrophes, right? We have people who are good at working with customers, so they're going to figure out what the customer wants in terms of requirements. We have a good process for actually going and writing these out. We have designers. These are going to be people who are very good at creating the system level description. So high level, what is the system doing? What are the boundaries? Things of that nature. Programmers, we're good at writing the code. Testers, these are very good people at catching faults, at figuring out the intricacies of where things will go wrong. But then you get into other aspects too. So people who are going to train users on how to use the system, right? People who are good at showing maybe non-technical people how to use software or hardware. You have people to maintain the team. Librarians, I haven't heard this term used much in industry, but I'm sure there are companies that use that. They're going to maintain the documents. More than likely, that's going to fall to your configuration management team. This is where you're going to have people managing your revision control, your project tasks, basically anything that's has to do with the overhead of the software engineering process. And interestingly, so this, again, clip-arty figure it's kind of a nice overview of where these people fall into the overall process. We see them all kind of going down to the maintenance line. So everybody at some point is going to have to deal with maintenance. Depending on your environment, you may have multiple roles too. So this is not the end all be all of the development team. Okay, so everybody's probably going to have their hand in it at some point, all of the various roles. Let's see. So I'm just gonna kind of check where we're at here, because I don't want to go too long. I'm gonna skip some of the history because we have to get into our Git demo. There is a key notion of software engineering and how it has changed. So there's this Wasserman's 7 key factors. This was a person who was very big in software engineering, IEEE fellow, very, very big name in software engineering. He identified these key aspects for software engineering and how it's problematic. So we have economics, we have to deal with user interfaces, networking, the waterfall method we'll talk about. It's very problematic for very quick changing projects. We'll actually talk about the processes next time. Object-oriented, dealing with the market. So these are all going to be different aspects that impact your project. Right? So one of the key things that we're going to do, and again, I'm just slipping slides. Yes, thank you for the warning. Is that we're going to try to abstract out our programs. And this is where you get into the object-oriented programming paradigm. Right? So I have a device of some kind, but I'm going to abstract it out into sensor level, into particular sensor levels. Your Java object-oriented programming, you have animal, or like dog is a animal, or cat is a animal. So we're trying to abstract things out. We're trying to generalize, and that kind of leads towards a better software engineering process, right? So I think what I'm going to do is I might actually, oh, we're actually pretty close to the end. That's good. I might just stop here because a lot of this is just repeating myself, and honestly, a lot of it is kind of common sense in a way, but it's mostly repeating the same points over and over and over again. The one thing to consider, though, is that I will stop on this slide, and now we're going to go to Git in a moment. There is not a schism, but it's more of a divide in software engineering. You're going to have two viewpoints for how to do it. You're going to have the real world way, so call it the empirical way. Basically, this is dealing with hard data, dealing with real systems, dealing with executing software in the field and seeing what happens. And then you're going to have the theoretical side, the formal side. This is where you're going to have your mathematical proofs, your mathematical models, not necessarily representative of the real world environment. So on the left side of this graph, and I'll make sure that I'm not mirrored here. Left side, no, left side, there we go. Right here, this is where you deal with the real data. Okay, I'm testing my system. I'm seeing all the inputs and configurations and user types, I suppose, that are actually interacting with it and seeing what the system is doing. This is your testing. On the right here, this is where I'm having, again, mathematical proofs. All of these models that we've created, we can simulate the system. And the term simulation is basically key here. I might run a model of an autonomous car, and here are all the different paths of execution it can go down, but at the end of the day, you're not seeing the real world. There is a place for both of these in the software engineering area, but one of them deals with real data, one of them tries to anticipate as much as possible mathematically. That's not a warning anymore. Thank you. So just be aware that there is this divide here. I tend to like this side of things, but a whole lot of software engineers like this side of things. So, and then yeah, the rest of it is just the real-time or the real world example stuff. So, high level where we are with software engineering. Next time we're going to talk about the processes and some of the models. But what we're going to go over now is your Git environment. So you have your homework due tonight, Intro to Git, and I'll have a lab manual for you after that's done. But what you have here is a GitHub repository that you are all going to be using for your term projects. So how it's going to work is that I'm going to have one of you, self-nominate inside your team. One person is going to fork this repository, meaning that they're going to take this repo and bring it into their user account. And then that person is going to add the rest of the team as contributors so that they can all check in code and commit code and all that kind of stuff. So the way this is going to look is that we have folders for your different artifacts. So these are your requirements. These are your models that we create, things of that nature. Our Friday is always going to be on Twitch. So pretty much every class is on Twitch unless if otherwise specified. The only reason we did it on Zoom or Blackboard last week is because I wanted you all to interact with each other. I will give you warning when I'm expecting you all to be on collaboration, I suppose. So you have a place for your meeting minutes. There's nothing in there right now, so you don't have to start doing them yet. There's a place for your source code, for your test cases that you'll be writing. You're going to create a GitHub website, so there's a place for that. The projects are licensed as GPL by default for you all. If you want a different license, you can always, of course, update that. And then a README, this is basically going to be your project report. So I have some placeholder things here, and you're going to be updating that later on as well. So if you've never used Git or GitHub before, and I'm using terms like forking and cloning and committing and all of that, so here I have an organization. So this is our 350 class, and this is the base repository. So what I will do is I'm going to fork it, and I'm going to fork it to my particular account. And what's going to happen is that's going to bring this project over into my user account. So now I have a copy of this thing, right? And I'm going to go ahead and change its name. So I'm going to go into the settings, update it, CIS350 project, term project, Fredericks. So now this is my project. It's still forked over from the base. So if I go over to the base here, I can see who forked it. My 641 class also forked this, by the way. I have this project, okay? So what I'm going to do now is I'm going to bring over my terminal here. I do everything terminal based with Git. All of my examples are going to be terminal based. I'm going to be using Ubuntu and Windows, so basically it's Bash. You can do Git with PowerShell. You can download Git for Windows, which is effectively like what I'm doing here. So what we're going to do, let's go to the root of my computer here. I want to clone this down to my machine. So I'm going to do got. I'm going to start mistyping here. Git clone and then this repo. So we're not going to go into the specifics of what Git is. You all got that hopefully with that little animated website thing. GitHub is the remote repository. I am now pulling this down to my computer. I have a local sandbox to work on. I kept spelling it get. You can set up an alias if you want, so get is git in your command line. So I have this repository here, and you actually see that a folder is created. So now if I go in there, can you all see this okay, or do I have to make this a little bit bigger? Let me make it a little bit bigger. So I have this project here. Oops. Let's do this. Clear it. Clear. CD CIS350. There we go. So if I do a ls, again, listing out the files here, here's everything that is actually up on that remote repository. Now, if I want to update the README, I'm going to use Vim, which if you have no idea what Vim is, it is the best text editor in the world, especially if you're an Emacs user. It's better than Emacs. And I'll die on that hill. It's got a massive learning curve, though, I will warn you. So let's say that I want to update this. So let's see, Frederick's team. Go, 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 go. All right. So the documents that are up on Git and GitHub, they're all in Markdown, if you're familiar with Markdown. So the headings are prefaced by pounds, bullets are asterisks. I can make a quote. This project is the best in the world. It will be something about procedural content generation. Oh, cool. Save it. Save it. Why are you not saving? Because, oh, there we go. So I've saved it, quit. I now have some changes. All right, so I updated this thing locally. If I type git status, I see that README has been modified. All right, so this process was not really clear in that website, which is why I wanted to show you. So I have to do a git add README, or I could just do git add period or git add asterisk to add everything that has changed. Cool. So now it is staged. It's ready to go. I have to give it a commit with a message. So updated README with team name. Creativity starting to wane, as you can see. Commit messages should be short but descriptive. Don't just do to do or updates or blah, blah, blah. You know, something very basic that doesn't tell you anything. Here's where you're telling your team members what changes you have made. All right, so I have committed this. It is committed locally. It is not pushed to the remote. So right now, if I refresh this website, we don't see any changes. My README is still the same. I have to do a git push. This is going to push my commits up to the remote. You might see git push origin master in some of the guides. That it means you're just overwriting the master branch, the head that you're currently at. Git push is going to update the current head. Depending on your project, I'm not expecting you all to do crazy branches or anything like that. You should just be able to deal with a fairly standard Git setup. Your mileage may vary here, basically. So git push. It's now going to ask me for my GitHub username. So it is still my old Oakland email address. You're not going to see your password on the terminal, but I typed it in. We're going to get a confirmation that it was pushed up, and we get our commit. All right, so now when I refresh my repo here, we actually see the commit message. I see my heading changed. I have my little quote here, description. So the stages here are basically to get the current status of your project. So let me mention this here. Do a git pull first. That will bring any changes your team members have made down before you start editing. Make your changes, do a git add, do a git commit, then do a git push, and you should be good. That's kind of your standard git process. And if you screw up and you make a whole mess of your local repository, the easiest way is to just delete your local folder and reclone it. So I will be putting a structure up for what your meeting minutes should look like when I start expecting you to be holding weekly meetings and writing minutes. I will let you know, basically. Does this make sense so far? Any questions at all? There's nothing stopping you from setting up your own Git repository. You know, if one of you are good with like Linux servers or servers, you can set up something called GitLab if you don't like GitHub. This is the easiest thing in the world right now. Yeah, so the only thing due tonight is that GitLab, so making sure you do those things so that you know what all these terms are that I'm talking about. Yep. When I put up the next homework, I'll send out an announcement for everybody. And what should happen too, let me pop this up as well before you all go. Hide this stuff. Let's see, so I'm gonna get a Git notification anytime something happens. So Discord will ping me when there were trolls on Wednesday. Yes, there were trolls on Wednesday. I muted them and then they got banned afterwards because they were spouting ethnic slurs and such. That was fun. Anyway, if you have any follow-up questions, office hours start in 10 minutes on Blackboard. Other than that, I will see you all Monday and hope you all have a wonderful weekend. I need some cool outro music. All right. Bye, everybody. I got you. Yes, thank you. Outro. Ooh. Ooh, ooh.
You know we finally here, right? It's Friday then. It's Saturday, Sunday. What? It's Friday then. It's
There you go.
Saturday, Sunday. What? It's Friday again. It's live Sunday.
Bye, everybody.